All right, so this is going to be a re-recording of the lecture from today. There were some technical issues regarding the video, so I decided to do a quick recap of what was covered in lecture today and post this to the course playlist. So a few quick announcements for the beginning of the video. For those of you who weren't able to make it today, homework 8 is due on Friday, so make sure you don't forget that. On Friday, you're also going to get assigned homework 9, which will be your final homework for the class, which will be due the following Friday. We do have our exam scheduled for Friday, May the 5th, starting at 8 a.m. We'll have our exam review on April 28th. For April 28th, that is when your final homework is due. Getting solutions that day, so no late assignments will be accepted. Also, it's the last day of the semester, so there wouldn't be time to collect them anyways. Also, one last note, make sure you don't forget to do your online course evaluation. Just email me proof that you completed it, and you will get homework points, bonus homework points added on top of your accrued average for the semester. Okay, so let's recap what was discussed today, which was specifically the analysis of discretely braced beams. So we will begin. Actually, let me go back a little bit. We'll begin right here with the discussion of the moment gradient modifier, C sub B. We were doing an example in the previous lecture on the computation of C sub B. Recall that C sub B serves to amplify your flexural moment capacity based on the fact that the moments are not uniform within a particular unbraced length. The equation is pretty straightforward. All you need are quarter point moments within a given unbraced segment, as well as the moment. Regardless of the sign, whether or not the moments are positive or negative, all of the individual values are taken to be absolute values. So everything that goes into the equation should be positive. We were working on the following example, or the example on this slide when we ended last time. All the loads here shown are factored, so we didn't have to worry about that. When you compute C sub B, you need to be working with factored loads. Excuse me. When we left last time, when we left on Monday, we had computed all of the moments, but we hadn't quite gotten the C sub B values. I've gone in and inserted the final expressions, and they were just computed using the equation that you see down here. It's incredibly basic and incredibly straightforward. Literally just plug and chug. So for segment AB, your MA, MB, MC are 75, 150, and 225 respectively, all in foot kips. And your maximum moment within that segment is 300 foot kips. For segment B, or BC, instead of your maximum moment being 300, your maximum moment is 337.5. Remember, you're thinking in terms of magnitude. So the largest magnitude moment within the segment BC is actually at C, so it's 337.5, not the 300. That negative 114.8 would be taken as positive in your C sub B calc. Same thing with, with C sub D. Take all those values as positive, and you'll get the C sub B values that you see there on the screen. Okay. Our main topic of discussion throughout the lecture today was the capacity or the analysis of a beam that is discretely braced. In order to properly discuss that, we need to make sure that we are comfortable with how a continuously braced beam behaves, namely that the maximum capacity or the capacity of a beam that is continuously braced is equal to MP. For when we discuss discretely braced beams, MP not only serves as the capacity at an unbraced length of 0, but it also serves as the maximum capacity, regardless of the buckling capacity or how C sub B can serve to amplify your capacity. MP is always taken as the max. So here's the fundamental beam chart, the fundamental beam curve, if you will. This is the flexural capacity of a steel wide flange cross section that's plotted as a function of unbraced length. So the first thing that you should notice is that as the unbraced length increases, the capacity tends to go down. For For instance, over here on the left side of the plot, we have a relatively high capacity right here, looking at M sub P right here. Whereas when we start to get to these longer unbraced lengths, you can see that the capacity has gone down. And that's a fairly common trend anytime you're dealing with issues of stability. When you have a section that is subjected to some type of compressive force, the longer it gets, the weaker it gets. Now, to be clear, we're not talking about the span length of a given beam. We're talking about the unbraced length of a given beam, or the distance between bracing elements, whether they be cross frames or beams framing in or something of that nature. Now, the capacity of a steel beam is broken up into three zones, if you will. The first zone over here on the left is the full plastic moment. And basically what this means is that if you have a beam that is really heavily braced, we're talking about really, really short unbraced lengths, so it braces all over the place. What this is essentially saying is that if you have a beam that has a lot of bracing, then it's really not going to be allowed to buckle, and it's really going to just be able to reach MP. So anytime your unbraced length is less than what we call L sub P and L sub R are anchor points that define the nature of the time your unbraced length is less than L sub P. That's a beam that's fairly heavily braced and is able to reach its full plastic moment. Once you get beyond L sub P, the beam is going to buckle. It's just a question of how it's going to buckle. Zone 2 is states that the beam will buckle in an inelastic manner, whereas Zone 3 is in an elastic fashion. A few things to note. So M sub R is really just a fancy term for the reduced yield moment. And all the reduced yield moment is 70% of Fy times the section modulus. And the reason for the 70% is to account for residual stresses, those locked-in stresses that you get in a section due to the manufacturing process. Also, in terms of the shape, the Zone 3 curve, the fact that it is in fact curved or sort of hyperbolic, all that is if I scroll up a little bit, all that is just this equation, the critical buckling stress. That Zone 3 is essentially what we derived. To keep everything simple from a behavioral standpoint, Zone 2 is just assumed to be a straight line fit between the plastic moment and the reduced moment. So that's your inelastic range, that's Zone 2. Most of the beams that we end up designing later will more often than not fall within Zone 2. Now, again, C sub B serves to amplify or increase your nominal moment. When you incorporate C sub B, what you're doing is you're getting a benefit. With using a C sub B equals 1 demands that every cross section of the beam must be able to attain its full capacity, and that's not necessarily the case in most typical loading scenarios. Really, only one point on the beam in most cases needs to be able to reach its ultimate capacity. So keeping C sub B equals 1 is not practical in a wide number of scenarios. So C sub B, for instance, if C sub B is, say, 1.5, it's going to take your capacity and increase it 50%. However, regardless of what C sub B does, capacity is always limited to your plastic moment. You cannot exceed M sub P. So your curve is always going to be cut off at M sub P. When you look at the equation for Zone 2 and Zone 3, they're always going to be a minimum of some computed value and MP for this reason. Speaking of some equations, L sub P and L sub R, again, are the unbraced length limits that tell you whether or not you're in Zone 1, Zone 2, or Zone 3. Sometimes they're called LTB anchor points, LTB for lateral torsional buckling. Sometimes they're called anchor points. The equations, particularly like L sub R, they look fairly nasty. Actually, the easier one on the slide to derive is L sub R. because L sub r is basically setting the equation that we derived equal to 70% of the yield moment and just solving for L. It's just algebra, actually, to solve for L sub r. L sub p takes a little bit of discussion and thought. There's a lot of analytical and experimental work that has gone into developing a simple expression for L sub p, a usable expression for when the onset of inelastic buckling occurs. Luckily, it doesn't really matter. L sub e and L sub r really need to be computed because you've got the specs, particularly the ZX table. L sub p and L sub r is computed for all of the shapes that you would be designing with. So once you find your shape, you can see L sub p and L sub r are already computed, and we can just use those. So as stated, we essentially have three zones. Zone 1 is the full plastic moment, so your capacity is just E times MP, or phi Fy Zx. Zone 2 is your inelastic range, which is a straight line fit between MP and MR. And elastic LTB is zone 3, and that's the same as the derivation that we saw before. So let's look at some equations. Here you can see the equation for zone 2. You can find this in chapter F of the spec. It's right within the first couple pages. The equation might look a little involved, but it really is just a y equals mx plus b, or a y minus y1 equals m times x minus x1. It's just really just a point slope formula. Again, that zone 2 is a linear fit. We can simplify this equation a little bit. Number one, we can write it in that familiar format where any time that you have those two quantities and that less than or equal sign, it's basically just the code's way of stating that it's the minimum of those two quantities. Also, I've replaced the 0.7 FYSX with R. Now, if you look at this expression and do a little bit of rearranging, you'll see a couple of things. So, if you look at table 3.2, you'll see that phi MP and phi MR are listed. There's also another term that's listed called B sub F, or BF, not B sub F, BF. Sorry about that. BF is an abbreviation for a beam factor, and it's really just another fancy term for the slope of the line in zone 2. If you look at this expression, that zone 2 is a line that goes from a change of LR minus LP on the x-axis and MP minus MR on the y-axis. So if you do a little bit of rearranging of this equation, the equation on slide 435 by substitution and a little bit of algebra, you can isolate that blue term on the bottom, which is really just the slope of a line, change in y over change in x. So we call that term BF, the beam factor. And we can use the beam factor to greatly simplify our expression. Instead of that long expression, we have what you see on the slide up on the top right. We're specifically going to use the one on the bottom because all of the phi values have been incorporated. So the nice thing is that if you use table 3.2 and you use the equation on the bottom to compute the capacity, you don't need to multiply by phi because it's already incorporated in all of the values that you need. Unfortunately for elastic critical buckling, first off, you do have to incorporate phi manually. You must incorporate it by multiplying by 0.9. You also don't have a nifty shortcut like you do with inelastic buckling. Unfortunately, because of the complexity of the equation, you just have to compute it. So the capacity, or the nominal capacity, is listed as the minimum of MP or section modulus times F critical. F critical is it's computed using the equation derived. It's a somewhat lengthy calculation. Fortunately, we have an example that you can follow here in a second. You just have to work your way through it, though. So to summarize, if you haven't already done so, this would be a great place to put a big scuff on your notes and highlight this. This is a very, very critical slide. Zone 1, which is between any time that the unbraced length is less than L sub P, your capacity is NP, or phi F Y Z X. For zone 2, your capacity is either the minimum of phi NP or that linear fit, and you can see the phi values have been incorporated, as well as the beam factor. Zone 3, it's either the minimum of phi NP or phi F critical SX. And notice the phi values have been incorporated. We're going to have to manually multiply that one out. C sub B is computed in using the equation shown. You can also use table 3.1, and it can be a very convenient guide. However, just be very, very careful. If you have a beam, for instance, that has a very substantial distributed load and a very substantial point load, then table 3.1 really doesn't work out very well. You're just going to have to grunt through your C sub B calc. F critical is as shown, and all of the appropriate LTB expression or constants found in 2. So we spent the rest of class today discussing the example that you see here on the slide. We have a W24 by 76. It's a simply supported beam, and it's being used to resist a concentrated load at midspan. Now, for the purposes of this example, the only dead load, if it were, that's on the beam is the self-weight. Now, 76 pounds per foot is not light as feathers, but compared to typical maximum concentrated loads at midspan, it would probably be fairly negligible. So what we're going to do for the purposes of this example is we're going to neglect the self-weight of the beam. And the reason we're doing that is just to make our lives a little easier when we do the analysis later. I don't want this example to be a C sub B marathon as much as I want it to be about computing the capacity. So by neglecting the self-weight, we're able to actually use a tabulated value for C sub B, and it makes our lives a little easier. Now, we're assuming that the beam is laterally braced at the supports and at midspan. Okay? So if I have a beam that's 20 foot long, or its span length is 20 foot long, then its unbraced length would be 10 feet. So in this scenario. So again, just making sure that you understand the difference between the span length and the unbraced length. Now we're going to do this problem for 3 separate cases. So case 1, a beam is 10 foot long. Case 2, the beam is 30 foot long. And case 3, the beam is 50 foot long. We're doing this so that we can explore the ability of the different equations. So let's go ahead and get into the math. How are we doing on time? Doing good. Okay. So first off, because the beam is simply supported with a concentrated load at midspan, and we're neglecting the self-weight, we can use table 3.1 to compute the C sub B. And one thing I should point out for this beam, we have the same unbraced lengths on both sides, and we have the same C sub B's on both sides. So looking at either expression, or looking at either segment, we're going to get the same capacity. Both segments of the beam have the same unbraced and the same C sub B, so we're going to get the same capacity. Looking that C sub B value up, C sub B is always going to be 1.67, so for these cases. So it's just an easy constant that we can use. Okay. So for analyzing a W24 by 76, we need some properties. So we're going to be doing this problem. We're going to be doing quite a bit of work on this problem. So I pulled some section properties from table 1.1 from the front of the manual. So I've got the section modulus, the center-to-center distance between flanges, that's h sub naught. I've got the radius of gyration for LTB, that's that RTS value. I've got your pure torsion constant, your Saint-Venant constant, that's J. So you can see those values listed there. I've got 176 inches cubed 23.2 inches, 2.33 inches, and 2.68 inches to the fourth, respectively, for those values. In Table 3.2, the ZX charts, the ZX tables, I've got the plastic moment, the LRF plastic moment of 750 foot kips. I've got the beam factor of 22.6 kips. Now that is correct. The units are kips because you're multiplying that times length to get foot kips. And I've also got my anchor points of 6.78 feet and 19.5 feet respectively. Okay, so case one's pretty simple. We have a beam that's 10 foot long, so its unbraced length is 5 feet. So since the unbraced length is less than LP, that puts us in zone 1 of the curve. Let me pull the curve up. So here's our curve. L sub P is about 6.7 something. 6.78. And L sub B is 5 feet, so there's our capacity, M sub P. Very simple. So M sub P for this section is 750 foot kips. That's our answer. Now for case 2, this is you can treat this as if it's an entirely different problem. So, we'll say 23A or 23B or 23C. Case 2, we have a beam that's 30 foot long. Its unbraced length at 15 feet. And if you look up in the top right, you'll see that's between the LP and the LR. So we're in zone 2. So that puts us in this range right here. Also note that because of C sub B, we could be cut off at M sub P. So that's something worth mentioning. Now you go through and do your math. Because you're in zone 2, you have that linear fit. So start plugging and chugging. Now remember, we're taking the minimum of whatever our computed linear fit is and M sub P. What we end up finding is that we compute a value of about 940 or so foot kips, but 750 foot kips is MP. So regardless of what we compute, we are cut off at MP. So this is an example of C sub B falsely predicting a grandiose capacity, if you will. The equations take that into account by saying it's the by stating that the capacity is the minimum of either what you compute or M sub P. However, when we get into design, this is one of the big reasons why multiple iterations need to be done in many times for design. So for case 2, our FEMN ultimately does end up being 750 foot kips as well. Finally, for for case 3, L sub B is 25 feet. That puts us square into zone 3. So we've got to do a little bit of math. One big note on the top, or sort of the middle of the right of the screen there. When you plug values into your equation, you're going to want L sub B to be in inches, not in feet. So your L sub B value is going to be taken as 300 inches. The reason why is if you look anywhere in your FCR equation where there's an L sub B, it's divided by R, or RTS. I mean, you can think of this like columns. You're basically computing an L over R, a slenderness value, if you will. You could sort of think of it as a torsional slenderness or a lateral torsional buckling slenderness value, this L over R. And L over R's need to be unitless, so you have to plug in inches. In fact, if you look at the expression, I know the equation looks a little nasty, but your units, your resulting units, are actually defined by whatever E is. Because if you look, here we have L over R, that's unitless. Here we have L over R, that's unitless. And here we have J divided by SXH naught. For I-beam, C is 1, so that's just a constant. J is in inches to the fourth. This is in inches to the third, and that's in inches. So this fraction's unitless. This fraction's unitless, which means everything under this square root is unitless. This is unitless, and then C sub B is unitless. The only thing with any units in the end is E, so that's what defines your answer. So plug and chug, and do a little bit of grunt work, and you end up finding that your critical buckling stress is about 39.2 KSI. Now notice that your C sub B was built into FCR. It wasn't built into FEMN, so don't multiply by that twice. However, you do need to multiply by phi. So multiplying by 0.9 FCR SX and comparing that against your your plastic moment will give you your final answer. Now, one thing to point out, your plastic moment is in foot kips. If you just take 0.9 times FCR times SX, that response will generate an answer in inch kips. So you need to divide by 12 to generate consistent units. Do that calculation at the center bottom of the screen, and you'll get an answer of about 517 or so, 0.5 foot kips. That's less than the bottom, so C sub B did serve to amplify our capacity in zone 3, but not enough to reach MP. So our capacity would be 517.5 foot kips. That's all we had for today. Next time we will discuss how to design discretely braced segments. So that's all we have. We'll see you.